Hello, welcome to our Semiconductor education program. I'm Vincent Chang. In this lecture, I'm going to present one of the most frequently used circuit theory in microelectronics called Miller Theorem. Let's consider a two-port network with feedback. So you can see an input port with two variables, the input current I1 and the input voltage V1. And also the output port with two other variables, output current I2 and the output voltage V2. But when you face a network with feedback, you have to consider two directions. One is the forward transmission from left to the right, and also the reverse transmission is the feedback transmission. So it gets complicated for most of the circuit analyzer. So Miller theorem can help us simplify this network with feedback. And simply we break the feedback component. We break the bridge and make the circuit equivalent to the original one. Just look at the right, it's the equivalent circuit after applying Miller theorem. So in the next few steps, I'm gonna prove the Miller theorem and let you know how this theorem comes from. Let's define a voltage transfer ratio, K. It's the output voltage V2 divided by input voltage V1. So based on the circuit on the left, the original circuit, we can write down the I1 equals V1 minus V2 over Z based on Ohm's law. And then let's replace the V2 by KV1. You can get this. And then if you look at the right, the I1 equals V1 over Z1. So there are three equal signs here. You can look at the first one, and also the last term. And just cancel out the V1, you can get this. So Z1, the input impedance, equals original feedback impedance divided by 1 over K. Since admittance is the inverse of impedance, so we can also express the Miller theorem based on the admittance. Let's try to find out what about the output impedance. So based on the original circuit, so I2 equals V2 minus V1 over Z. So look at the circuit on the right. So I2, if we substitute V1 by V2 over K, we can get this. And look at the circuit on the right. So I2 also equal to V2 over Z2. Z2 is the output impedance. So if we cancel out these two V2, so we can get the output impedance, the relationship between the output impedance and the original feedback impedance. It's the Z divided by 1 over K. What is K? The forward voltage transfer ratio. Okay? So also I'm showing you the impedance part, the impedance relationship. So let me show you one example, very classical example to apply Miller theorem. This is called 741 bipolar operational amplifier. It's very complicated. And then if you look at the blue part, there's a feedback component. And the circuit on the top is the equivalent circuit of the complicated original bipolar operational amplifier. The green corresponds to the green point, and The red corresponds to the red point. So now I'm asking you to pause for 1 minute to apply Miller's theorem and find out what's the input capacitance of the gain stage and also the output capacitance of the gain stage. Let's pause for 1 minute. Did you get it? So let's apply Miller's theorem to this circuit. So we break the feedback capacitance into two parts. The one on the left is input capacitance. The one on the right is the output capacitance. So what's the expression for these two capacitances? The one on the input side should be CC divide all times. Divide all times. So the capacitance is proportional to admittance and inversely proportional to impedance. So it should be multiplied. So the one on the left, I didn't put this on the slide, so you can maybe pause and write down CC, the one on the left should be CC multiply 1 minus K. The one on the right, the output capacitance should be CC multiply 1 minus 1 over K. So here's the summary. So again, this lecture, I try to give you the one of the most frequently used circuit theory in microelectronics, and it tells you where it comes from and how to apply it. Here's the end of the lecture. Thank you for watching.